Today, we are looking at something pretty incredible, a manufacturing technology that literally builds solid metal parts layer by tiny layer, using nothing but pure, focused light. I mean, that sounds like something straight out of science fiction, right? But it's happening right now. It's a process that can repair and even create some of the most advanced, high-performance components on Earth. So, how does it work? Let's get into it. The core technology behind this magic is called Direct Metal Deposition, or DMD for short. At its heart, it's a really powerful form of additive manufacturing. Think of it as 3D printing, but instead of plastic, you're using fine metal powder and a seriously high-energy laser to build complex parts from scratch, or even repair old ones. So here's what we're going to cover in this explainer. We'll start with how it all works, then we'll meet the two competing laser technologies that power the whole thing. We'll see what each one is good at, and finally, figure out how you pick the right tool for the right job. Okay, so how do you actually go from a file on a computer to a solid metal object you can hold in your hand? Let's walk through the process. It's really a four-step dance. First, an engineer designs the part in a 3D CAD file. Then, software slices that digital model into thousands of super thin layers. After that, another piece of software creates a precise toolpath, like a roadmap for the machine to follow for each and every layer. And finally, the deposition head gets to work, following that path, melting the metal powder with a laser, and building the part layer by painstaking layer. That laser, that's the key. It provides all the energy to make this amazing transformation happen. But here's the thing, not all lasers are created equal. In the world of DMD, you've got two major players, two titans competing for dominance, continuous wave and pulsed wave. The best way to think about them, it's like a powerful, roaring blowtorch versus a razor-sharp surgical scalpel. They deliver energy in completely different ways. So a continuous wave laser, or CW, gives you a steady, uninterrupted stream of energy. It's always on, always delivering the same power, kind of like a hose turned on full blast. A pulse wave laser, or PW, is the total opposite. It delivers its energy in these incredibly fast, incredibly powerful bursts with tiny moments of nothing in between. And trust me, that one fundamental difference changes everything about what these lasers can build. First up, let's talk about the workhorse of the industry, the continuous wave laser. Its steady, constant power makes it absolutely perfect for big, consistent jobs where what you really need is strength and speed. So why do people love CW lasers? Well, it's all about reliability and power. That constant stream of energy creates a large, stable pool of molten metal, and that results in really hard components with nice, smooth surfaces. You know, as a bonus, their design is a bit simpler, which usually makes them a more cost-effective choice for a lot of industrial work. One of its killer apps is repairing parts that are just way too expensive to throw away and replace. Think of something like a turbine blade from a jet engine. With a CW laser, you can precisely add new material right where it's worn or damaged, basically bringing it back to life. And get this is what's really amazing. Studies have shown that parts repaired with CW lasers can actually have up to 25% higher tensile strength than the original metal. How? Well, the super-fast cooling process creates this really fine-grained structure in the new material, making the repaired spot even stronger than it was to begin with. Now, those same qualities, that high hardness and that smooth finish, make CW lasers absolutely perfect for creating custom-designed medical implants. You can take a patient's CAT scan and fabricate a titanium hip joint, for example, that fits them perfectly and has incredible strength and durability. Okay, now let's turn our attention to the second titan, the pulsed wave laser. This is the specialist. It's all about precision, delivering just immense power in tiny, tiny fractions of a second. We're talking nanoseconds here. The sheer amount of energy packed into each pulse lets PW lasers do some pretty wild things. They can instantly vaporize material, even metals with ridiculously high melting points. And that gives engineers an unbelievable level of control, opening up this whole new world of microscopic and super detailed manufacturing. For instance, PW lasers are the only choice for a technique called pulsed laser deposition. What happens here is a high-energy pulse zaps a target material, instantly turning it into a cloud of plasma. That little cloud then settles onto a surface, creating an ultra-thin film that can be just a few nanometers thick with the exact same chemical makeup as the original target. It's incredible. These lasers can also create these highly controlled, porous structures. So instead of laying down a continuous line of metal, each pulse deposits a tiny, perfect, ball-like drop. By controlling exactly how those little spheres overlap, engineers can build these intricate, super lightweight lattice materials with absolute precision. Think of things like scaffolds for biomedical engineering. So there you have it, the steady powerhouse and the precision specialist, the blowtorch and the scalpel. So, which one wins? Well, the reality is, there is no single champion. The research is really clear on this. The conversation isn't about which laser is better. It's about which laser is better for a very specific task. The quality of your final part all comes down to picking the right tool for that specific job. And this table really brings it all home. If you need brute strength, speed, and smooth surfaces for big repairs or tough implants, the CW laser is your go-to. It's the blowtorch. But if you need microscopic precision to create things like nanofilms or complex porous structures, then the PW laser is the only choice. It's the surgical scalpel. You see, understanding these two laser technologies isn't just about manufacturing things we already know. It's about pushing the very boundaries of material science itself. When you can control matter at this fundamental level, you're opening the door to creating materials with properties we've only ever dreamed of. It really just leaves you wondering, what's just around the corner? What will we build next?